Hello students, so today we will study atomic structure question part 7. Disclaimer. Disclaimer, the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the images. So what are we going to do today? So we are going to practice questions from 54 to 60. Question number 54. Question number 54 says that the radiation is emitted when a hydrogen atom goes from a higher energy to a state of lower energy state. The wavelength of one line is in visible region of atomic spectrum of hydrogen is 6.63 into 10 to the power minus 7. The energy difference between the two states is, so your options are A 3.0 into 10 to the power minus 19, option B 1.0 into 10 to the power minus 18 joule, option C 5.0 into 10 to the power minus 10 joule, and option D 6.5 into 10 to the power minus 7. So you have 10 seconds to solve this question. Your time starts now. Okay, now let us see the solution. The question says that we know it very well that whenever there is a transition from higher to lower energy, then the amount of energy by which the two states differ, that much amount of energy related photons are emitted. Okay, now it is given that the wavelength of one line in visible region for its atomic spectra of hydrogen is this. So this thing is given that when we see a visible region, say transition, means the emitted light falls in the visible region, then it is seen that the wavelength is found to be 6.63 into 10 to the power minus 7. So the energy difference between the two states is, right? So I have told you that for a transition to occur, there must be a, for the emission spectra to be recorded, there must be a transition from higher state to lower state. So what are those? What is the energy between those two states that is being asked? So answer is A 3.0 into 10 to the power minus 19 joule. Let us see how we'll solve it. So first of all, the energy difference between two states is assumed as delta I, and using the relation of say Einstein relation, we have written it delta I is equals to hc by lambda. This is the amount of energy that is differed between the two states, and that much amount of energy is emitted in the form of light, whose say wavelength is lambda. Now, if you put all the values, so Planck's constant, the speed of the light, and your lambda value, which is given as 6.63 into 10 to the power minus 7 meter. So if you put all of this, you will get your energy difference, which is 2.9 into 10 to the power minus 19 joule. Or we can write it approximately 3 into 10 to the power minus 19. So this is your answer. So this was only asked that what is the energy difference between the two states. So we have calculated it using this very simple relation. Okay. Moving on to the next question. Question number 55. Question number 55 says that the given set of quantum numbers for a multi-electron atom is 200 1 by 2 and 200 minus 1 by 2. What is the higher allowed set of n and l quantum number for this atom in its ground state? Your options are A, n is equals to 2, l is equals to 0. Option B, n is equals to 2, l is equals to 1. Option C, n is equals to 3, l is equals to 0. And option D, n is equals to 3, l is equals to 1. So you have 10 seconds to solve this question. Your time starts now. Okay, now let us see how we can solve it. First of all, what is the question? So the question is saying that we are given a set of quantum number for multi-electron atom. Multi-electron means more than one atom, and those set of quantum number are 2001 by 2, 200 minus 1 by 2. Now you have to find that what is the next higher allowed set of n and l quantum number for this atom. So this is this one of the state. Two states are given. Now after this, what will be the highest state of quantum number? You have to give the n and l value. Okay. So the answer is n is equals to 2 and l is equals to 1. How we have said that? So whenever we are saying that what is the number value of L for a given value of n, then it is n minus 1, right? And what is the value of m for a given value of L? So it goes to minus L to plus L, and it has a total of 2L plus 1 value. And say this spin quantum number has always two values, minus half and plus half. Now for the given two sets, that is this one and this one, the next highest state will be n is equals to 2 and L is equals to 1. How it is so? Because it is being written that the quantum number set is n, so this is n value, L value, m value, and 1 by 2 is s value. So this is which orbit subshell? This is 2s orbit, right? See, this is 2s orbit. So after 2s, we have the 2p, and for 2p, your n value is 2 and l value is 1. So it is as simple as that. So here, one thing you have to remember, I think, which is that this is, and this should be n. So this is the order. This is a way of writing the order, that is n, l, ml, and ms or s, which is principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. Okay. Now moving on to the next question. Question number 56. Question number 56, again, it is given that in a multi-electrons atom, which of the following orbitals described by the three quantum number will have the same energy in the absence of magnetic and electric fields? This is quite a conceptual thing, which is the set of quantum number are n is equals to L, L is equals to 0, M is equals to 0. B, n is equals to 2, L is equals to 0, and M is equals to 0. Option C. So not option. Set set number C, n is equals to 2, L is equals to 1, M is equals to 1. D, n is equals to 3, L is equals to 2, M is equals to 1. And E, n is equals to 3, L is equals to M, and L is equals to 2, M is equals to 0. What are the options? The options are A, D, and E, B, C, and D, C, B, and C, D, B, and A and B. So why I'm telling the option? So that you get a time to analyze the question, right? Okay. So you have 10 seconds to solve this question. Your time starts now. Okay, so let us see how we can solve this question. For that, first we will see what is the question. So the question is saying that you are given a multi-electron atom. Okay, multi-electron, again, more than one electron is called a multi-electron atom. And we have to see that out of the given orbital, means the given orbital. So if you want to know the orbital, all description of orbital, you need only three quantum number, because spin is for the electron, especially for the electron, I would say, not for the electron, especially for the electron. So you have to say that which of the following orbital will have the same energy in absence of magnetic and electric field. So why it is written? So why this? The reason behind it lies in your definition, right? So when we are saying the magnetic quantum number, it means that that quantum number is visible, or that energy state is visible in the presence of magnetic field. So quite complicated to think about, but you can think it like that whenever the electrons come under the influence of magnetic field, they get splitted into different energy states. But in the absence of that, there is no such thing observed. Okay. So the correct option is D and E. So orbitals are said to be degenerate, which occur when their n plus L value are same. Okay, clear? So for D and E, n plus L value is 5 and 5 both. Okay, so orbital having quantum number n, L, and m this thing, and n, L, and m this thing, right? So they will have the same energy. Okay, in the absence of magnetic field and electric field. So what happens? So for a given n value, all the energies are same initially. But what happens when we apply magnetic field? this shell gets splitted into different orbitals. Okay, and different for first different subshells and different orbitals. Now their orientations are different. Okay, the electrons which are present, their sense of rotation and the orientation are different. But when there is absence of these fields, then all the electrons in a given shell will have the same energy. So that thing is mentioned. Okay, so it's a bit complicated to think of, but you can simply think it in this way, that in the absence of magnetic and electric field, all the electron lying in the same shell will have the same energy value. Okay, as simple as that. Okay, moving on to the next question. Question number 57. So what is question number 57? Question number 57 says that consider the following sets of quantum numbers, which is for 1, so n, l, m and s values are given. So 1, 3, 0, 0 plus half, 2, 2, 2, 1 plus half, 3, 4, 3 minus 2 minus half, 4, 1, 0 minus 1 minus half, and 5, 3, 2, 3, 3 plus half. Which of the following set of quantum number is not possible to see? Options are A, 2, 3, 4, option B, 1, 2, 3, 4, option C, 2, 4, 5, option D, 1 and 3. So you have 10 seconds to solve this question. Your time starts now. Okay. Now let us see the solution. So the question is asking that out of this, which set of quantum numbers is not possible? So for that, you have to simply think of the all the rules that you know about quantum number, that what are the possible quantum numbers that you can have in okay, so if you know about the quantum numbers and what are the acceptable values of L for a given value of n, and what are the acceptable value of m for a given value of L. So if you know this much, then it's good to go to solve this type of question. Okay, so let us see the answer. So it is 2, 4 and 5, which is this one, and this one. So let us see how it is. So for any orbital, again, what is the allowed n L value? So it goes from n to n minus 1. Okay, so it is n minus 1 values are possible for L. So it goes from 0 to n minus 1. So suppose if it is n value is 3, then it will go from 0, 1, 2. Okay, 0, 1, 2, these three values are possible, right? Similarly, for a given value of m, 2L plus 1 values are possible, which goes from minus L to plus L. For L, n values are possible, I would say, and that value is how what for suppose I am saying that okay, I am taking 1s orbital, right? Sorry, first shell. Now first shell means the value of n is 1, n is 1, so therefore there will be only one value of L, that is 0, and it starts from 0 to n minus 1. So n minus 1 means 0, so it's 0 only. Similarly, if you are going for the second shell, suppose, so what are the possible values of L? So it will be, there will be two values that will be possible, because the n value is 2, so two values of L will be possible. And what are those values? For that the formula is 0 to n minus 1. So n is 2 here, so 2 minus 1, 1, so 0 and 1 are the two possible values. Okay, as simple as that. But we get, when we go for the m values, so those values can go from 2L plus minus L to plus L. Okay, and how many such values are possible? So 2L plus 1 values are possible. Suppose if you are taking the p orbital, so p orbital has a value of L as 1. So what are the possible values of m? So it is 2L plus 1, which is 2 into 1 plus 1, which is 3, right? And what are the there are three, means there are three values possible of ml. And what are those values? So the values are minus L to plus L. So that is minus 1 to plus 1, because L was 1. Okay. And S value is fixed. It depends upon the electron state, which is minus half and plus half. You don't have to worry about it. It does not depend on orbit, orbital shell, anything. Okay. So, so in case 2, if you see here, you have to see that which one is not possible. So if you case 2, if you see here, then the n value is L. Sorry, the n value is 2. And the L value is also 2. But L values goes from 0 to n minus 1. That is 0 and 1 are the two values which is possible for the second shell. 2 is not possible. 0 and 1. These are the only two values that is possible. Right? So this is wrong. Second, for the fourth one, if you see here, then n value is L. Good. So what are the L values that are possible? So 0 and 1. Okay, these two values are possible for the first shell. So 0. Okay, well enough. Now what are the possible values of M? So if it is 0, that is your s orbital. So s orbital has only one ml value, which is 0, because it goes from minus L to plus L, and since it is 0, therefore only one value of ml is possible, which is 0, but it is written minus 1. Notice. Last one, if you see here, then n value is 2 and L value is greater than 2. Okay, so you should remember this always, that L value cannot be greater than n value. Okay, it should always be less than n value. It cannot be equal to, neither it can be greater than. So for this case, these two are not possible. And for say the value of m, so if you talk about the value of m, then the magnitude of m value should not exceed your L value. You can take this also. Okay. So with this, we would say that okay, these three are possible. But why these two are not possible? So see, n value is 3. So L value can go from 0 to 2. Okay. And what are the possible values for m? If L value is 0, it is 0 again. Similarly, for n value 4, we can take 0 to 3. So 3 is taken. And for L value of 3, there are 6 values. 12 plus 1. So through 3, 6 plus 1, 7 values are possible. So that is minus 3, minus 2, minus 1, 0, plus 1, plus 2. So minus 2 is given. Okay, then discuss. So this one and this one are okay. Now moving on to the next question. Question number 58. Question number 58 says that for the electrons of oxygen atom, which of the following statement is correct? Options are Z effective for an electron in an 2s orbital is the same as Z effective for an electron in a 2p orbital. Option B, an electron in the 2s orbital has the same energy as an electron in the 2p orbital. Option C, Z effective for an electron in an 1s orbital is same as the Z effective for an electron in the 2s orbital. And option D, the two electrons present in 2s orbital have same spin quantum numbers but of opposite sign. Okay, so you have 10 seconds to solve this question. Your time starts now. Okay, now let us see the solution. So you have to find the correct statement. So the correct statement is this, that the two electrons present in the 2s orbital have spin quantum number ms but of opposite sign. Okay, so this is true. So if you are going for one orbital, suppose you are going for 2s orbital, then two electrons can be maximum accommodated in that, and that can have half magnitude, value of ss half magnitude, and it can be minus half or plus half, either of them. Okay, so what is the solution? So first of all, if you took the first statement, which is saying that electron in 2s and 2p orbital have same screening effect. No, it is not true, because means if you're taking the 2s, then inside means excluding the outer orbitals, the inner orbitals are 1s, right? So 1s is also contributing to that shielding effect. If you consider 2p, then 2s is also contributing to that, right? So they have the different screening effect. Okay, so this is true. Hence, their Z effective is different. Okay, the electron in 2s and 2p have different screening effects. So Z effective of 2s is greater than the Z effective of 2p. Therefore, it is not correct. Okay, energy of 2s orbital is less than energy of 2p orbital. So it is not correct, because n plus L value is what? Okay, so n plus L value is what? N plus n value is uh, 2 plus 0, which is 2, and here 2 plus 1, which is 3. Okay, so this is the thing. They are not same. So it is next is C is given that Z effective of 1s and 2s is same, but it is not true, because there are different electrons that are present inside it. So this is true. Okay, so these are the correct statements that is given. Okay, these are the correct statements instead of the statement that we have seen earlier. Moving on to question number 59. Question number 59 says that Which of the following statements about the electromagnetic spectrum is not correct? Option A, infrared radiation have larger wavelength than cosmic rays. Option B, the frequency of microwave is less than that of ultraviolet rays. Option C, X-rays have have larger wave number than microwaves. And option D, the velocity of X-rays is more effective than that of microwave. So you have 10 seconds to solve this question. Your time starts now. Okay, now let us see how can we solve it. So first of all, you have to look out at the correct statement. Sorry, incorrect statement. So the incorrect statement is this, which is X-ray speed is more than that of microwave. Let us see how it is incorrect. Because all of the radiation that we see, they have the same speed. So this is always should be in your mind that all radiation that we see will have a speed of 3 into 10 to the power 8 meter per second. What else would be required to do this question? First of all, you must know the order of wavelength of all the spectrum or the order of energy, either of them. If you know one of them, you can go and calculate it for each of them. So if your energy order is going from left to right, okay, I'm just taking a case. If it is going from left to right, then your wavelength order will go from right to left. And since wavelength is inversely proportional to your cell energy, but the energy order and frequency order and wavelength order, wave number order, this all will be having the same order, but your wavelength will be in the opposite order because wavelength is inversely proportional to these three, that is the energy, frequency and wave number. Because wave number is nothing but 1 by wavelength. Again, energy is E is equals to hc by lambda, and nu E is equals to h nu, therefore nu is equals to c by lambda. Again, nu is inversely proportional to lambda. So nu, that is frequency, energy and your wave number, these three are inversely proportional to say wavelength and directly proportional to each other individually. So you just have to remember one series for each of the radiations, either in accordance with the wavelength or wave number or frequency. Okay, you can take either of any of them. Okay, but the thing you should remember is very important is that every radiation has a speed of this, which is 3 into 10 to the power 8 meter per second. Okay, now moving on to the next question. Question number 60. So question number 60 says that consider the following statement. First statement, psi square is a measure of electron density at a point in an atom. Statement number 2, radial probability function, which is 4 pi r square psi square, gives the probability of finding the electron at a distance r from the nucleus regardless of direction. Statement 3, the shape of an orbital is defined as a surface of constant probability density that encloses some large fraction of the probability of finding the electron. So you have to select the correct statements. Your options are both 1 and 2. Option B, both 2 and 3. Option C, both 1 and 3. And option D, all of these. So you have 10 seconds to solve this question. Your time starts now. Okay, now let us see what is the answer. So first of all, these are the statements, right? So these are the three statements. You have to see that which one is correct. So first is saying that if you take the wave function of the electron and just square times it, okay, then it gives electron density. Second is this saying that if you take the radial probability function, which is this one, this is the radial probability function, okay. So if you just take this thing, okay, then it gives the probability. So this function, if you just plot it against the distance, then it is being said that it is irrespective of the distance that you are taking. The third which is being said is that if you take the shape of the orbital, that is the dumbbell shape or your spherical shape or double dumbbell shape, it is nothing but a surface of constant probability, means it is just a probability function plot, okay, that encloses the large fraction of the probability of finding the electron. Okay, so all of these are correct. How? Because psi is what? Psi is your wave function. If you just square times it, that is your amplitude, and that amplitude is nothing but a probability density. You must have seen this multiple times. Okay, that psi has no physical significance. It is just the wave function, but you just square times this, you will get the probability of finding the means it is gives the probability of finding the electron. Second is this radial probability function. It is irrespective of the direction that we are taking, right? And its third statement is what? So whenever you plot this probability density, you plot this thing, right? To plot this thing, you will get various points. So if you just when you take multiple and you can say large number of these points of this function, then you get this shape, which is the shape of the orbital. So this statement is also correct. So with this, we have completed all the questions. Thank you.